So the simplest population model is where the growth of a population, or let's see, the dPdt, the rate of change of the population is proportional to the population itself. And this is like the simplest case. You can just solve it as a separable differential equation. By the way, k is the proportionality constant. So or you can say that's the growth rate. Okay, so if this k is big, that means it's going to increase very fast. If k is small, then it's going to increase very slow. Okay. Let me quickly solve this. I can multiply by dt here and divide by p here, so I get 1 over p dp equals to k dt. So I separated. K is just a constant, so on this side I have t only. On this side I have p only. So I separated between t and p. And then you integrate. This gives you ln of p. Whereas on the right side it gives you kt plus c, by the way. And you take exponential both sides, and you get e and l cancel, so you get p equal to e to the kt, and then I use that trick, rewrite c plus c as e to the c, and just redefine this as our new c. Or if you don't like that, you can just call it c tilde, whatever. So I can just say, oh, p is equal to a constant multiple of e to the kt. So that will be the solution of such differential equation. And what is it saying? It's a function which is growing exponentially. Right? Now, if you also had an initial condition, p of 0 equals to p naught, if such a condition was given, then you can plug that both sides and say, when p value is p naught, I want, and t value is 0, t value is 0, I need this to be satisfied, but e to the 0th power is e, k times 0 is 0, e to the 0th power is, not e, sorry, e to the 0th power is 1, so I get p0 equal to c, which means the solution is p equals to p naught e to the kt. Now let's think about what this graph might look like. So initially, you're going to have,
Bless you. Bless you.
Thank you.
initially you're going to start with p0, and it's going to increase exponentially, just like that. Okay? And this was actually the population model that people a long time ago was thinking when there was this Malthusian prophecy about how the humanity is going towards doomsday because there's just simply too many people increasing without bound. Yeah. Yes?
I'm sorry, where'd you get the lowest equation? The one on the bottom?
This one, oh wait, I got the c equals to p naught, right?
Yeah.
So I replaced
Oh,
the
you
c
just
by
put-
p naught. Okay, so p is equal to p naught e to the kt. So that will be the solution to this differential equation with this condition. Okay? It means that initially your population is p naught, and it just increases without bound. It's exponentially increasing. It's increasing very fast. Okay? All right. However, real population doesn't really work that way, right? Because people also die, right? This is just saying, oh, if you have more people, then they make more people, so the rate of change will be as big as that, right? So here's a second model of population growth where you have this concept of a maximum capacity. So here's how you think. So the first observation is the following. It's same as before. The rate of change of population will be proportional to how many population you already have, right? So suppose there's a city, there's a lot of people living in it, and if you have more people, then there are more couples available to make more babies, and when more babies are created, population grows quickly, right? So you can just say rate of change of the population will be proportional to the population already in the city, right? However, there's also another factor here. The second thing that you have to consider is that there is something called the maximum capacity that that city can hold. It's just some number which we have to determine that tells you this is how much it can hold, right? So there's this maximum capacity, and if you subtract the population from the maximum capacity, then you can also say that the growth rate should be proportional to m minus p. Now, let's think about what this really means. If population is very close to the maximum capacity, what should happen? This value will be very small, right? And it really makes sense because suppose you have a city where the population is getting very, very close to the maximum capacity. That means even though there are more people available to make more babies, because of the problem with the environment, maybe there's too much pollution, lack of food, whatever, people can't live a long life. So a lot of people will die, right? So the growth rate will kind of be stalled when it gets closer and closer to this maximum capacity, right? So this is the second observation. And what's even more shocking is what if for some reason population itself went over the maximum capacity? Then this value will be negative, right? That means the growth will be negative. In other words, it's something like this. If you have a city where there's even beyond the maximum number of people it can hold, what would happen? Well, people will start killing each other, I don't know. Or I guess realistically what's going to happen will be
They move out.
they will move out, right? They'll move out of the city so that they're going to experience this negative growth, right? So putting these two together, you have the following equation which says dp dt is proportional. Again, whenever you change these proportional thing into equation, you have to use this proportionality constant k. And you say, oh, it's proportional to p, but it's also proportional to m minus p. Now you might ask, shouldn't we use two k's, k1 and k2? But it doesn't matter because if k is some unknown number anyway, so if I have k1 and another k2, they multiply to give you k, so it doesn't matter, okay? So we get this single equation, and there's a name for this equation. It's called the logistic differential equation, okay? And the reason for this will be clear once I solve it, okay? All right, so let's try to solve this differential equation. What type of differential equation is this?
First look.
Separable, first order linear, exact?
Exact.
Separable.
Separable. Why is it separable? There's no t at all. So you can basically take this and move it to that side and move the dt here, and you've separated t and p. Right? The two variables are separated. Okay. So let's do that. I'm going to divide this much to the left, so I get 1 over p times m minus p dp. I'm going to move the dt over to the other side so that it's multiplied with k. So I've successfully separated the p variables on one side and t variables on the other side. And k and m are just constants, so it doesn't matter which way, which side it belongs to. I mean, if you want, you can divide by k and it's still separated. Okay? It doesn't matter if k is here or there. I like k being on the top rather than the bottom, so I just moved it here. Okay, now we integrate. This side is easy to integrate, but this one is not. To integrate this, you need something that you learned in Calculus 2, partial fraction expansion. That's what you need. Do you remember that?
Yeah, I remember that.
All right.
That's like right after.
Okay, you should definitely review that. In order to be successful in differential equations, you have to know how to do every integral that you learned in Calculus 2. Okay. All right. So. Yeah, let me rewrite the differential equations because I still, it's important. So dp dt is k times p times n minus p. This is the differential equation we want to solve, and this is how you're going to solve it. And here's a rather quick and dirty approach to doing the partial fraction expansion of this. I'm just simply going to take 1 over p and 1 over n minus p, and I'll try to add them together. Okay. And because I know something that you don't, I know that when I combine this, I'm going to get something similar to this. Okay. So let's see how it works. So in order to add them, I need common denominators, so I multiply n minus p top and bottom. And for the second one, I multiply p top and bottom, so that I have the common denominators. Now I can combine the two into a single fraction. What do you get? M minus p plus p is? M. Wait, but m is just a constant, right? Yeah. So this is m times 1 over p times n minus p, which is exactly what I have here. Okay? So we're going to do that trick again. I like m over p times n minus p. I want this m. So how do we make that happen? Multiply by m, right? And divide by n. So this is same as this. And I know that this is equal to what? Sum of these two, right? It's 1 over p plus 1 over n minus p dp. Now what's the integral of 1 over p dp?
ln.
Yeah, 1 over m should still be there. ln of p. And let's see if you know how to do this one. What will be the integral of this one? F prime over f, anyone? If you differentiate this by p, what do you get?
ln of n minus p.
No, it's just the L. Yeah.
Negative ln of m minus p. Why? Because if you differentiate this by p, what do you get? Differentiate m by p, what do you get? M is a constant, right? So if you differentiate m, you get?
mp. I mean,
If you differentiate m, you get?
Zero.
0. If you differentiate p, you get?
Negative 1.
Yeah, it's because it's negative p. If you differentiate negative p, you get negative 1. So derivative of the downstairs is negative 1, and that's what you want on the top. Well, I have 1. So what do we do? Instead of plus 1, I rewrite this as minus minus. Right? Then, now I can say this is f prime over f, which is ln of the denominator. Now, do you also remember this fact that if you have log and if subtracted, what do you know?
They're divided.
it's same as dividing, right? So that's what you get on the left side. Let's look at the right side. The left side, it's 1 over m ln p over m minus p. What do you get if you integrate k dt?
KT.
Kt plus c, right? Some constant. And we're almost there. We can just now all we have to do is just solve for p. Okay. All right. So multiply by m. So you get ln t m minus p equals to k mt plus cm. But since m is just a constant, I'll just just keep it as c. It's really c times m, but I'm just going to call it as c. Now I have to get rid of ln, so I take the e both sides. So I get p m minus p equals to e to the kmt times e to the c, and again I'm just going to call this as e c itself. Okay, I still need to solve this for p. I want p is the population. I want p as a function of t. So I have to solve this for p. It's not that easy. Basically, this is how you think of the left side. P over m minus p is p minus m minus p plus m over m minus p. How's that? They're the same thing, right?